In the last video, we looked at trigonometric functions of angles, even if they're bigger than 90 degrees. In this video, we're going to be looking at trigonometric identities. At first, these two ideas might seem kind of disconnected from one another. You could be forgiven for thinking that they're kind of unrelated. But actually, as we'll see in the not too distant future, they are actually related. So let's talk about what an identity is first. Here's one. It's just a statement that one side of an equation and the other side of an equation are equal, that they have the same value. So while this is a very, very simple example, it's an identity. Here's another one. The cosecant of theta is equal to 1 over the sine of theta. Now this is a trigonometric identity just because it involves trigonometric expressions. I can actually prove that this one is true. Let's start with the idea that the cosecant of theta is defined as hypotenuse over opposite. And then let's say, well, I can write hypotenuse over opposite as 1 over opposite over hypotenuse. And then let's say that that's 1 over, well, opposite over hypotenuse is the very definition of sine of theta. And there I have it. This is a very basic, very simple proof. I'm going to be asking you to prove some things later in the quarter. Not quite yet, but pretty soon. So it's really not too early to start talking about how to do a proof. I'll show you how I did this one, and then as we talk about the other trigonometric identities, we'll prove a few of those as well, and I'll show you how I do those. In this case, what I did was start with one side of this equation. This is the thing that I'm trying to prove. I cannot use the fact that these two things are equal in my proof. I haven't shown that they're equal. That's the whole point. I can't use this equality in my proof, but what I can do is take one side, write it a different way, write it another different way, and keep doing that until I end up with the right-hand side. What I've got here is that the left-hand side is equal to cosecant of theta, which is equal to something else, which is equal to something else, which is equal to something else. And that is equal to the right-hand side. So I have shown that the left-hand side is equal to the right-hand side by producing a bunch of intermediate steps. This is always the goal of a proof. All right, that was a little bit of a sidebar, but let's take a moment and talk about these identities that we already know. The cosecant of an angle is 1 over the sine of the same angle. The secant of an angle is 1 over the cosine of the same angle. And the cotangent of an angle is the same as 1 over the tangent of the same angle. Now, by virtue of the fact that these things are in fact reciprocals, I could also say that the sine of an angle is equal to 1 over the cosecant of the same angle, and so on. Cosine is 1 over secant, and tangent is 1 over cotangent. These are called the reciprocal identities. I think you could probably figure out why. There are actually a couple of others. We learned this as well. The tangent of an angle can be found by taking the sine of that angle and dividing it by the cosine of that angle. By virtue of reciprocation, the cotangent of an angle can be found by taking the cosine and dividing by the sine. These also count as reciprocal identities. Let's take a moment just for fun. Well, we might not all consider this fun, but I'm going to take a moment, I think it's fun, and prove this identity just to show you another example of a proof. When I write out a proof, what I might write to start with is the claim that I am making, which is that the cotangent of theta is equal to the cosine of theta over the sine of theta. Then I'll write my proof. As I start my proof, I make the observation that I'm not allowed to use this equality. Otherwise, I would have one line. If this is true, this is true. There's not much in it there. But this is actually what I'm trying to prove. And mathematical proof leaves absolutely no room for debate. So I can either start with the right-hand side and mess around with it until it looks like this, the left-hand side, or I can do the other way around. In this case, I think I'm going to start with the right-hand side. So I'm going to write right-hand side equals cosine of theta over sine of theta. That in turn equals, by definition, adjacent over hypotenuse over, that's the cosine, adjacent over hypotenuse, over opposite over hypotenuse. You don't need to color code these. I'm going to do it just because it's easier to see. The cosine is this whole numerator, and the sine, the denominator there, is all of this. Okay, so now I've shown you a different way to write cosine over sine. What I'm going to do now is use a little bit of algebra to simplify this expression. I have adjacent over hypotenuse divided by opposite over hypotenuse. That means times hypotenuse over opposite. I can then cancel my hypotenuses. Hypotenuse, I'm not sure what the plural is there. I'm going to rewrite this step so that you can see what I had before and what I have after I cancel. Because I'm writing this for somebody else to read, I want to leave as many breadcrumbs as I possibly can. So here I've indicated that this line here is another way to write this double fraction, this complex fraction. But I took a separate step to indicate that within this expression, I have a couple of things I can cancel. Now that's kind of personal choice. I'm trying to keep it as informative as possible. As you write proofs, I would recommend that you do the same. In a class like this, your audience is me, but in reality, your audience would be another mathematician. And so you need to write your proofs so that somebody else can come along who has the same level of knowledge as you do and understand what it is that you're trying to convince them of. You won't have the benefit of being able to say verbally, as I'm doing on this video, that the reason I'm taking this step is because I want to rewrite this way. This is by definition. You only have the record left by your handwritten proof. So take every step and leave every breadcrumb that you possibly can. When I grade these, I'll be reading them not as though I was the audience, but as though another student was the audience. Do I think that your argument has convinced or could convince another student in our class, for example? So write your proofs as though you're explaining them to someone else in the class, even if you don't know who that is. Okay, we're not finished here, so let me keep going. Now I'm going to write the step that shows the simplified fraction. I have adjacent, once I've canceled my hypotenuses, over opposite, and that is equal to, by definition, the cotangent of theta. And that's my left-hand side. So again, what I've done is started with the right-hand side and said that it was equal to what I was given for the right-hand side. This right-hand side is equal to, I was given this. This is equal to this. This is equal to this. This line here is equal to the next line. That one is equal to this. This is equal to cotangent. Cotangent is the left-hand side. So ultimately, I have shown that the right-hand side is equal to the left-hand side. Something that's very important to keep in mind as you write proofs, or as you read proofs, or as you watch videos about proofs, is that I am trying to convince you that the cotangent of theta is equal to the cosine of theta over the sine of theta for any angle, right? I can't put different angles in here than I have here, but whatever angle I pick for theta, this statement will always be true. So if theta is pi over 2, and pi over 2, and pi over 2, this will be true. These two sides will be equal. If theta is 17 pi over 97, then it will still be a true statement. And the reason I can make that claim is because I have done all of my work using the generic angle theta rather than a specific one. That's a very important take home. All right, so there's all of our reciprocal identities. I'm going to go to the next screen to talk about the next type of identities. The next type of identities we're going to be talking about are called Pythagorean identities. Rather than tell you what they are and then prove that they're true, I'm going to show you how the first one is derived. And then once we've derived the first one, that means built it from scratch. Once we've derived the first one, I'll show you how to use algebra to derive the second one and the third one. We'll start by just drawing a generic angle in the first quadrant. I don't really care about all four quadrants in this case because I'm just going to use this to show you where the formula comes from. And then I could show you or prove to you that it can be applied to any of the four quadrants, but I don't think I'll take the time to do that. We'll just see if we have time. Now that I have an angle in the first quadrant, let's drop that vertical and give ourselves a right angle. And then we'll label it as we normally do. This angle here is theta. This is r, because remember, we're sort of pretending that this is on a circle and that that's the radius of a circle. The height of the triangle here is the distance from the x-axis up to some y value. So it has the length, that line segment has the length y, and the x-axis, on the x-axis, we can go from 0 all the way out to this point here. We're going to call that x. This is just how we've been labeling these triangles. It's in standard position. So the initial side of the angle is down here on the positive x-axis, and the terminal side is up here. We're calling that the radius. We're calling that r. Before we get into the rest of this description, I want to make one point here, and that is that because this is a right triangle, I can write this statement: x squared plus y squared is equal to r squared. That's just the Pythagorean theorem based on the particular triangle that I have written right here. Now, I'm going to make a couple of observations. One is that x over r, when you square it, and then add it to y over r, also squared, is equal to x squared over r squared plus y squared over r squared. And that's x squared plus y squared all over r squared, because it's a common denominator. Well, I said up here that x squared plus y squared was r squared, so now I have r squared over r squared, which is 1. Well, that's cool and everything, but so what, right? But what is x over r, and what is y over r? Well, y over r is the sine of theta. So I have the sine of theta squared. Plus, I'm kind of writing backwards here. I'm going this term plus this term is equal to this term plus x over r is the cosine of theta squared. So as it happens, just by using some algebra, I have the cosine squared of an angle plus the sine squared of an angle is equal to 1. That's the Pythagorean identity. It's the primary Pythagorean identity. Now I'll take a second and give you some more notation. Instead of writing parentheses, cosine theta parentheses squared all the time, we can write, and this is just a convention, but this is what this means, we can write the cosine squared of an angle. These two things are equivalent. You can use either one, but you will see in the textbook and in most of the videos that I do and all over the internet, this is the form that you'll see for that. Cosine squared of theta means the cosine of theta squared. So whatever the value is for the cosine of theta, square it, okay? Now, if I use that notation, I can rewrite this expression and its equation and its equality as cosine squared theta plus sine squared theta equals 1. Most of the time, it's written the other way around. Sine squared plus cosine squared equals 1. And this is the primary Pythagorean identity. Let's go ahead and highlight that. And in fact, I think I'll use a different color. I'll use green for this one. This is the primary Pythagorean identity. I'm highlighting it in green. We're going to add to it. We're going to have a list of 3 of these. But this is the only one I'm going to derive by using this idea here. For the other 2, I'm going to start with a copy of sine squared of theta plus cosine squared of theta equals 1. And I'm going to divide both sides of that equation by cosine squared of theta. Okay, now I'm going to do backwards algebra, or arithmetic really. This is just the addition of 2 fractions with a common denominator. I'm going to write it as 2 separate fractions. Sine squared of theta over cosine squared of theta plus cosine squared of theta over cosine squared of theta equals 1 over cosine squared of theta. Remember from algebra that a squared over b squared can be written as a over b squared. And I'm going to do that next. I'm going to write this as sine theta over cosine theta all squared plus cosine theta over cosine theta all squared. If I think of 1 as 1 squared, I could do that here as well. 1 over cosine theta all squared. Now, we have some other identities that we've already learned and we can already kind of own and use however we want that come into play here. The first one, I think, that most obvious one, is that anything divided by itself is 1. So I'm going to write this as plus 1. And I'll go ahead and square it because all I'm doing here is showing that this thing inside here is 1 and that I haven't dealt with this squaring process yet. That's going to be equal to something over here, and I have to find another way to write this here as well. Let's do the left-hand side first. The sine over cosine all squared. Well, sine over cosine is tangent. And I can write tangent of theta all squared, or I can write tangent squared of theta. And 1 over cosine is secant. So again, I can write secant of theta all squared, or I can write secant squared of theta. This is another one of the 3 Pythagorean identities. But notice that I don't need to memorize this one. I've got this one here, and when you leave this course, if you remember nothing else, I would bet money on the fact that 5 years from now, you'll remember this formula. If you remember this one, all you need to do to get to this one is divide both sides of this equation by cosine squared. Equally, if we divide both sides of the equation by sine squared, let's see what happens. I'll make another copy. Sine squared of theta plus cosine squared of theta equals 1. And I'll divide both sides by sine. This time I'm going to take a little bit of a shortcut because when I divide both sides by sine squared, I'm going to have the same phenomenon as I did here, where I get sine squared plus cosine squared all over sine squared, and then I'm immediately going to split that up into 2 fractions. So I can say divide both sides by cosine squared or by sine squared, or I can say divide every term by sine squared or cosine squared, and I get the same thing. Now I'm also going to skip the step that has me pulling out the squared, right? And dealing with that separately. I'll skip that step because we've learned now that sine squared over cosine squared is the same as sine over cosine all squared, and that's tangent squared. So sine squared over cosine squared is tangent squared. Kind of a shortcut there. Sine squared over sine squared is just 1. Cosine squared over sine squared is cosine over sine all squared. Well, cosine over sine is cotangent. So cosine squared over sine squared is cotangent squared. And 1 squared over sine squared is 1 over sine all squared. Well, 1 over sine is cosecant. So there's another Pythagorean identity. But that one I just took from the first one as well. So again, if I had this one, I could get these other 2 by dividing this one through by sine squared or cosine squared, depending on which one I want. Now, I proved for you the identity that the cotangent was equal to cosine over sine. I didn't prove this trigonometric identity, but your textbook does. I would encourage you to read that. It's on page 496, at least in the edition that we're currently using. It's under the blue box called Fundamental Identities, where those first 5 trigonometric identities, the reciprocal identities, are listed, and the 3 Pythagorean identities. They just state the 3 Pythagorean identities, and then they prove the first one. I didn't do that. I derived it for you instead. They're using similar logic to prove it. They start with the statement, sine squared plus cosine squared equals 1, and then they rewrite sine squared plus cosine squared. So take a look at that and make sure you understand the difference between coming up with the formula and proving an identity. Okay, now that we have these identities, we can refer to them whenever we like, and we can use them in other problems. So what I'm going to do now is go to the next screen, write a summary of the identities that we've learned so far, and then I'm going to use them to work through a couple of examples of how you might use identities, the places that you might put them to use. Okay, here's a summary of the identities we've learned so far. These are the reciprocal identities. I've never really understood why we need this cotangent, because tangent, we already know, is sine over cosine. So 1 over tangent, which is cotangent, is going to be equal to 1 over, or 1 divided by, sine over cosine. Well, that's 1 times cosine over sine. So cotangent is cosine over sine. So I've never really understood why we need a separate listing for that particular identity, but it's in the chart, it's in the table in your book, so I'll just leave it there. Now, there are many, many times in the course of using trigonometric expressions that we want to be able to change the way a particular expression looks. Probably the most common of these is that I can write sine of theta using cosine instead of sine. I also will frequently want to be able to write cosine using sine and not cosine. So here's how I'm going to do that. Sine squared, remember that's just the sine of theta squared. Sine squared plus cosine squared equals 1. That's just one of my Pythagorean identities. If I subtract cosine squared, subtract the quantity that would be cosine squared from both sides of that equation, I get sine squared equals 1 minus cosine squared of theta. If I then, I forgot my theta. If I then take the square root of both sides of this equation, I get the sine of theta equals the square root of 1 minus the cosine squared of theta. Now, this is not 1 minus cosine theta, because the square root of a squared plus or minus b squared is not a plus or minus b. Please remember that. It's a very common algebraic mistake. This is not true, okay? I'm actually going to erase it because I don't want to leave it on the screen. It makes me nervous even just looking at it. I can do the same thing with cosine. I can say sine squared of theta plus cosine squared of theta equals 1. Subtract sine squared from both sides. That gives me cosine squared of theta equals 1 minus sine squared of theta. If I take the square root of both sides, I get cosine of theta equals 1 minus sine squared. Again, that's not equal to 1 minus sine, so don't go there. But this is another, you could argue that this is another identity. But there are so many algebraic things that I can do with these identities that it would take pages and pages and pages to write them all down. And there's no way you could memorize them all. So it's actually very handy to memorize a very few basic ones. And there will be a few more beyond these, but these are really the crucial ones. And then from these basic ones, realize that you can write one trigonometric expression, one trigonometric ratio, in terms of a different one, the way we did here. Let's do another one. Let's try to write the secant of theta in terms of the sine of theta. There are a couple of approaches you might take. One is to notice that you have the secant squared of theta here. You can write that as tangent squared plus 1 and then take the square root of both sides. It turns out that's really messy, and I actually haven't been able to figure out how to verify that it's equivalent to the way that I'm going to do it here. So I'm going to do it this way, and then I encourage you to try it the other way and see if you can figure out how to make them equal, or see if you can figure out how to demonstrate that the two different answers that you get, two very different looking answers that you get, are actually equivalent. I'm not going to do that here, though. I'm going to start with this other identity that has a secant in it, 1 over cosine. So I'm going to write that the secant of theta is equal to 1 over the cosine of theta. And that is equal to, as we know from this work here, 1 over, since the cosine is equal to the square root of 1 minus sine squared, I'll just replace cosine with the square root of 1 minus sine squared. And actually, that's it. I'm done. This expression here has sine in it. It no longer has secant in it, and it no longer has any other trigonometric expression, just sine and some constants. So that's what we mean when we say write secant in terms of sine. That's it, done. Now, in this case, I was able to just do that in a couple of steps. In other problems, you might take more steps, and you might find that your intermediate steps, the steps in between here, have more than just one trigonometric expression in them. You might have something that's got a sine and a secant, for example, or a cosine and a tangent. And you have to keep going. You have to keep converting one or both of those expressions into something that's in terms of the expression that your goal expression. Now, your textbook actually claims that you need to be able to use this skill in order to do example 6. I'm going to walk through example 6 just as it is in the book, but I'm going to do it a different way to show that you don't really need to use this skill for that particular type of problem. You certainly can do it that way, but I find it a little bit cumbersome and kind of unnecessary. That said, this skill is important. It's very important to be able to say sine squared plus cosine squared, forgot my theta there, equals 1. Therefore, sine squared can be written as 1 minus cosine squared. If you see sine squared in something that you're working on, you can replace that with 1 minus cosine squared. If you see sine, then take the square root of both sides. And you have sine is the square root of 1 minus cosine squared. Rather than memorize this, actually this one you probably will, but rather than memorize it, you really only have to memorize this relationship and recognize that this phenomenon occurs sometimes, that if you subtract one or the other of these from both sides, you get a sort of variation of the original identity. And that's really what we mean when we say write one trigonometric expression in terms of another. All right, let's take a look at the example. Let's see, what page is that on? Example 6 is on page 497. I'll write it out, but I'm going to talk through it in a different way than the book approaches it. Okay, here's our question. If the tangent of theta is 2/3 and theta is in quadrant 3, find the cosine of theta. Well, if the tangent of theta is 2/3, and we know that tangent is opposite over adjacent, then it could be either that the opposite of the angle is 2 and the adjacent is 3, or it could be that the opposite is 2 and the adjacent is 3, but both negative. In that case, opposite over adjacent gives me a negative divided by a negative, and that's a positive. It cannot be the case that the opposite is 2 and the adjacent is 3, where we're in quadrant 4, because in that case, we're down below the x-axis, and the y value here, which is my opposite, that's negative. A negative divided by a positive is a negative. The tangent is given as a positive 2/3. It also cannot be the case that I'm in quadrant 2, because here I would have a positive opposite, positive 2 here, but a negative adjacent. So there again, my opposite over adjacent would give me a negative 2/3, and I have a positive 2/3. So it's definitely not the case that I'm in quadrant 4. And it's definitely not the case that I'm in quadrant 2, but I could be in either quadrant 1 or in quadrant 3. And that's the reason that this problem has to state that theta is in quadrant 3. They have to give you this information in order for you to know which quadrant you're in, because it could be either of those two. All right, so we know that the tangent is 2/3 and that theta is in quadrant 3. So let me actually also erase this piece. And then what I'm left with is the reference triangle for the situation that was described here. The tangent of theta is 2/3 and theta is in quadrant 3. And all I have to do now is use that triangle to find cosine of theta. Well, cosine of theta, let me choose a different color here. Cosine of theta is adjacent over hypotenuse, and this is my reference angle, so that's my theta. Adjacent is -3, and the hypotenuse, well, I don't know what the hypotenuse is, but I do know that I'm working with a right triangle here, and so I can use Pythagoras to find the third side here. I have a side length of 3, and I could go ahead and call it -3 if I wanted to, because when I square it, it's going to become positive anyway. And I have a side length of -2, and that's going to be equal to my hypotenuse squared. This is 9 plus 4, that's 13. So the hypotenuse squared is 13. That means the hypotenuse is root 13. I could put it here, I could put it in my diagram, but there's my cosine. It's -3 over root 13. I don't need to go to all the lengths of converting this and changing the, what did they say? You have to write cosine in terms of tangent. Well, you really don't for this type of problem. There are times when it's very handy to be able to write cosine in terms of tangent, and there are ways to do that. You can read through the example in the book to see how they did it, but you don't always need to. And in fact, I think it's very tedious to have to do it when you can do it really quite as easily as this. The textbook does example 7 in much the same way as I've done example 6. The question there is, if secant of theta is 2, which would be 2/1, and theta is in quadrant 4, find the other 5 trigonometric functions of theta. So there, instead of just asking you to find one, they've asked you to find all of the others. But once you have the 3 sides, you can find all the others very easily. Here, though, they sketched a triangle, they used a reference angle, and they used the fact that theta was in quadrant 4. Once they had their triangle and their 3 sides, they just found the other 5 ratios. So they pretty much did that problem the same way as I did example 6. All right, in this video, we've looked at trigonometric identities. We've kind of created a table of those that are really very important, and although they're very basic and fairly straightforward, they're really worth memorizing or putting on a note card or something so that you have access to them easily. They'll come up a lot, and you're going to want to have pretty ready access to them. In the next video, we're going to talk about areas of triangles. Again, this feels a little disconnected from things we've done before, but it's related, or it's connected at least. And so in that video, we're going to look at the area of a triangle. You know the formula for the area of a triangle is 1/2 times the base of the triangle times the height of the triangle. But what if you don't have the height? What if you have the base and one of the other sides? Can you still find the area? And it turns out that with trigonometry, you can. So that's what we're going to talk about in the next video.